Welcome to this presentation. My name is Marijn Nijenhuis. This talk is on high precision mechatronics and in particular the use of flexures for obtaining motion stages that can move fast and with very low hysteresis. A quick introduction. I'm an assistant professor, just started before COVID at the University of Twente. So I'm at the chair of precision engineering. I did my PhD on modeling of flexure mechanisms, and in this line I'm continuing and I'm developing this research line further now. The full professor at our chair is Dennis Brouwer. You see him pictured here. Some of the material in this presentation stems from the courses that our chair teaches. Some of it stems from earlier research projects that we did with people that were affiliated in the past to our chair or are still currently associated with the group. At the chair we have expertise on topics of design, control and modeling, and in some of our projects you see that these three pillars interact so that we can do interesting research that targets mechatronics applications. The material for this presentation stems from courses that our chair, that our group teaches now or in the past, and it also is based on research projects of the past and current. For this talk, the topics that I have in mind are the following. I would like to start with a brief introduction into precision engineering to mention what the field is about. And then to introduce the topic of parallel kinematic manipulators and the use of flexures in order to be able to discuss our recent work on the T-Flex hexapod manipulator. So that's the goal that we're working towards here at the end. So first on precision engineering. Now the field of precision engineering doesn't target one particular machine, but it's really about designing any machine with very high accuracy. And high accuracy means that we have to make sure that the tolerances during manufacture are very low, that the machine operates very repeatably and in a very stable manner over time. So that's very well isolated from any disturbances from the environment. So in a way that we understand the causes and effects in the machine very well. So in the past, if you would ask people what is an example of precision engineering, it would have varied over time, depending on what the high-tech machine at the time was. So in the past, it could have been the manufacturing of, say, the steam engine. Further back, it could have been guns, or for instance, the manufacture of locks in doors. Very old example is this one. This is the dioptra. And there has been reported use of this device already centuries before Christ. Hero of Alexandria was one who wrote a book on this device. It's a measuring device, essentially a tube with two sides at both ends, and it can be pointed at objects. For instance, in the sky for astronomical purposes. And it's got, at least for the time, a very precise screw. So by counting the number of turns of the screw, you would be able to derive angles with this device, and from that you would be able to derive distances. So it could also be used to lay out infrastructure over large distances. A more modern example, also astronomy, is this one, pictured on the left here. This is the extremely large telescope, which is currently under development. It's being built in Latin America, in Chile. They expect first light, as they call it, in 2028. This is a reflecting telescope that's going to be Earth-based, and the primary mirror in this one will have a diameter of over 39 meters. It will contain close to 800 hexagon segments. These all need to be extremely flat and well aligned with respect to a certain object that needs to be observed. To do that, each of these segments, of which there are close to 800, will have at least 3 degrees of freedom actuation. So it's an extremely complicated and highly accurate system. Here you see the envisioned system pictured in size with respect to the Colosseum in Rome. Another example, this is essentially a large-scale physics experiment. It's a very large interferometer. So this is a detector for observing gravitational waves. So whenever gravitational waves pass the Earth, supposedly the strain is on the order of 10 to the power minus 21. So that's extremely small. And to be able to resolve such a small change, the interferometer needs to be very accurate. So the arms here that you see pictured are 4 kilometers long, and within an arm the light bounces back and forth a couple of hundred times to make the interferometer more accurate. You can imagine to get the ability to detect strains of this small magnitudes, it needs to be isolated from any disturbance from its surroundings extremely well. It's a very tricky and a challenging precision engineering example. This is the LIGO detector. This one is in Livingston, Louisiana. There's another one in Washington State as well, and also in Europe. Here, an example from the Netherlands. This is from company ASML, who does semiconductor lithography. So this is a machine that produces wafers with the high-tech semiconductors of the current age. So this machine uses ultraviolet light, and it's close to X-ray wavelength with 13.5 nanometers. The motion stages in this system, for instance the wafer stage, needs to be positioned with sub-nanometer accuracy in order to be able to produce these chips with extremely high performance. Then to the topic of parallel kinematic manipulators. I would like to talk about what these are, first by explaining what they are not. So if we look at these examples, these tend to be examples of robots that people think of when they picture one. So here on the right hand side you see a 6-axis robot that's being used to pick and place beer bottles. This is what is referred to as a serial robot. So it's a manipulator architecture that's referred to as a serial one. And it's serial because the connection from the ground to the end effector of the robot is a single link. So the joints are in series with each other, meaning that, for instance, the base joint and the base actuator needs to move and carry all of these joints on top of it. So it has some advantages, some disadvantages. Some obvious advantages is that it has a fairly large workspace compared to the size of that robot. Here we see an example. This is a cinematic render of a serial robot here playing table tennis. The reason I'm showing this is to observe what the size of the robot is in relation to the workspace it can reach. So here you can see the feel for the size of the robot needed to reach the workspace of half a table tennis table. This is a serial robot. Now here you see the serial robot on the right hand side. So these are 6 axes, and you can see that it's a stacked collection of actuators and joints, and it can move that end effector in all kinds of ways. On the left hand side we have the same version but as a parallel kinematic configuration, and it's a bit different in some ways. It can also move that end effector in 6 degrees of freedom. One thing to observe here is that the actuation is located at the bottom. So we can see that the parallel robot has got its 6 actuators all stationary on the ground, meaning that the moving mass in the parallel kinematic manipulator is fairly low, and it can be beneficial if you need high accelerations. What is also important to realize is that the workspace to build volume ratio of the parallel kinematic manipulator is not as good as the serial one. We can also see that in the next one where again we have a table tennis playing robot, but now it's first of all a real one, was actually built, and it's a parallel one. So here you see the table tennis robot the parallel version. You can see that the robot itself is much bigger compared to the serial one that we saw before. The reason for that is, of course, related to the maximum angle that you can make in the joints and the entire configuration, whether or not it allows motions or whether it will lead to collisions. So some of these examples of serial and parallel robots we saw, and they have various advantages, disadvantages. So we mentioned that the moving mass for the parallel robot is much better because the actuators can be at the base and the successive joints don't need to carry all of these things in the same chain. If there are errors in the system, for instance, introduced in the joints, maybe they're rolling or sliding joints, then in the serial one they accumulate up to the end effector, whereas in the parallel one they would average out. With the parallel one, it's possible to get a fairly good stiffness at the end effector, provided that the joints are well designed. Now, some of the elementary kinematic joints that we see and that we will be talking about more, these are pretty standard ones, but it would be good to quickly mention the names of them. So these are essential kinematic joints that perform elementary functions. So for instance, the prismatic joint we see on the left, that's a 1 degree of freedom translational joint. So it allows motion along the axis and it provides constraints in the 5 other directions. Same for the revolute joint, but then the motion it allows is a single rotational degree of freedom. The universal joint is a 2 degree of freedom joint, sometimes referred to as a Cardan joint. And then there's the spherical joint. The spherical joint blocks all 3 relative motions of translation, and it allows all 3 relative motions of rotation of the joint. Now this is a Stewart-Gao platform, and this is a parallel kinematic manipulator architecture that is fairly common. It's usually referred to as a Stewart platform, but actually Gao was the first one to build it, to use it. And he was an engineer at Dunlop in the United Kingdom. On the right-hand side, you can see that particular hexapod in action testing a tire. So they use it for tire testing purposes. And it's been used for a long while that way. Now, the way this is a Stewart-Gao platform. This is a very commonly used parallel kinematic manipulator architecture. On the right-hand side, you see the first hexapod that was used, and it was actually built by Gao. So it's commonly referred to as a Stewart platform, but Gao was actually the first one to build it. He was an engineer at Dunlop, and they used it for testing tires. So in that figure on the right, you can see a little tire under that platform of the hexapod. The architecture looks something like this. So on the left-hand side, we see 6 arms that go from the base to the end effector. So we have multiple chains making it a parallel configuration. We can see that in each arm there's a universal joint at the base, providing 2 degrees of freedom, then a prismatic sliding joint halfway, and each arm is connected with a spherical joint to the end effector. With this Stewart-Gao platform, it's common that you see the actuator in the prismatic joint, so halfway as an extensional thing in these arms. With 6 actuators, this manipulator can manipulate its end effector in all 6 degrees of freedom, if the arms are oriented well. So that's what you see here. You see the end effector moving in all 6 degrees of freedom. So it's a very versatile robot architecture for that reason. If you look at commercially available hexapods, so robots with 6 arms that have 6 degrees of freedom, they can be exactly the Stewart-Gao configuration or some variant of it. You often see a trade-off between range of motion and repeatability. So these are 2 hexapods that are available commercially. For instance, the one on the left. This one has very high repeatability, so it's a repeatability below the micron, but then the range of motion is going to be small. And if you need a large range of motion, usually you'll have to sacrifice the repeatability of the system, which you see on the right-hand side. And it comes down to the type, one of the things it comes down to is the type of joints that are used. So for the ones with the high repeatability, often you see that flexures are being used in these joints, and the ones with larger ranges of motion tend to use sliding or rolling contacts, such as linear or ball bearings. Now we think that this gap between, or this trade-off between ranges of motion and repeatability can be bridged such that we can obtain a hexapod that will do both. Very good repeatability, so a low micron number, and also a fairly large range of motion. So for that, we'll look at a few recent developments in flexures for doing that. And I'll first briefly talk about what we mean when we're talking about a flexure in this sense. So here you see an example of a simple beam that is, you could think of it as a plate. It's very thin, and it's got a length and a width, as you see pictured here. You can imagine if we're moving it along the orange arrow, the stiffness will be small because the thickness is small for this beam, so it can bend easily. Conversely, if you're loading it in the plane, so vertically, because of the geometry of this system, the stiffness will be much higher. So in that direction, it will be able to provide stiffness and provide some load carrying capability. So it really stems from the geometry of the part. So as an example, this way it can move easily because of the low stiffness. This direction, it provides high stiffness. We can combine several of these flexures to create, say, a revolute joint, but flexure-based. And several of these revolute joints can be put together in a mechanism. As you see here, this is a 2 degree of freedom planar manipulator, a parallel kinematic manipulator, which was built years back in our lab. Looks something like this. So it contains 9 to 11 of these flexure-based joints, depending on how you count them. And what would be interesting here is to see the size of the workspace of this system relative to its build volume. So if we make it move, you can see that the workspace is around 10 by 10 centimeters. It's this shaded area right here. You can compare that to the size of the manipulator. And of course, if the angle that could be achieved in the joints would be bigger, then the arms don't need to be as long, and you could increase the ratio of the range of motion to the build volume of this system. So here we're using these flexures, and these flexures operate purely on the principle of elastic deformation, and that brings about several advantages. The important ones are that there are no effects like friction and play in the system. So because it's purely elastic deformation, there's no sliding or rolling contact. And that makes that you can use these in situations where you shouldn't contaminate the environment, for instance, such as vacuums, or where it's very hard to maintain the system, or where you don't want to use oils for lubrication. So maintenance-free and contamination-free. Because it's pure elastic deformation, the hysteresis in the system is going to be very low. Here's another example. This is an example of a revolute joint that's a bit more complicated in terms of the topology. So if we look at what this system looks like, you can see in the internal part there's many more parts, and some of the challenges in the design are in making sure that the parts don't collide and that the maximum stress is not exceeded. This is also a revolute joint, but it has some beneficial properties in terms of the stiffness that it provides in the off-axis direction. So the support stiffness is more favorable for a design like this compared to the elementary one of the 2 crossing leaf springs that we just saw. To get a sense of the internal part here, this is a quick 3D print of this one. The red is the part of the flexure. So you can see that the structure in the internal part is fairly elaborate. We have other designs In the lab, this is an example of a spherical joint. We will look at it in more detail later on. It contains these so-called folded leaf springs. They're also beneficial flexure components. This is what a printed version of that one looks like, and it's actually a spherical joint. So it can produce 3 degrees of freedom rotational motion. So some key points of flexures that we saw so far, they rely on elastic deformation, and that brings about some beneficial properties, meaning no contact, no friction, no play, and therefore a very repeatable motion. Of course, because it is elastic deformation that's happening, it's going to be limited in the range of motion that you can make before the maximum stress is exceeded or the maximum strain occurs. What we haven't talked about so far, but which is a big challenge in the design, are non-ideal stiffness characteristics. So we saw that we want to have a low stiffness in the directions of intended motion and a high stiffness in the directions of support. But it's not always the case, and in particular there's non-linear effects that mess up these ideal stiffness characteristics that we would want to have. So some of the design challenges lie in dealing with these nonlinear effects. Now, as an example of that, here we're going to look at this single beam, and that's loaded in this lateral direction. So this is the direction of support, and if the beam is not deflected, so straight and flat as it is right now, the support stiffness is fairly high on account of the geometry of this system. And you can imagine that if we deflect this blade and then provide that force, some twist will develop in the system, and the stiffness for torsion is fairly low for such a blade, such a leaf spring, which means that with deflection, the support stiffness of this structure decreases. So you get this typical bell-shaped curve of decreasing support stiffness, which ideally shouldn't happen. Ideally, this support stiffness was high throughout the range of motion, in this case a deflection. This is for a single beam, but also for more elaborate flexure designs, you do still tend to see behavior that support stiffness decreases with the range of motion. What are ways around it? To give an indication, there are design ways, topology ways to go around that. So one way is to add an additional structure, like you see here, and this will reinforce the torsion stiffness while not affecting the bending stiffness too much. So if you add this torsional reinforcement, it can still deflect fairly well, like you see right here. So this stays relatively unaffected. But now in the deflected state, when lateral force is applied, the torsion stiffness is much higher, so we don't see the drop in support stiffness as much. And to improve this further, you could use this idea further and add an additional torsional reinforcement to it, like you see here. So this is one of the ways in which a designer can influence the properties of these flexure systems. Then to size, to give dimensions to such a flexure, it's getting important to figure out what the right dimensions are, because obviously in some sense you want to make the material as thick and as wide as possible, but at the same time the maximum allowable stress should not be exceeded. And there are other trade-offs that you see in these designs. We have had some recent innovations in these flexure joints, and these flexure joints are fairly good for obtaining a large range of motion while maintaining support stiffness. And with these joints, we saw an opportunity to create a hexapod that can combine a relatively large range of motion for its workspace while providing a decent support stiffness. And because all of the joints are flexure-based in the system, the repeatability is going to be very good. So it's going to be a submicron repeatability. The principal designer for this system, the T-Flex, was Marijn Nijenhuis. He was a PhD student at the Chair of Precision Engineering, and all of the details of this hexapod can be found in his thesis, which you see pictured here. So this is what that system looks like. This is also Marijn Nijenhuis in the video, and you can get a feel for the size of this T-Flex robot like this. So it's A hexapod, parallel kinematic manipulator, meaning that the platform can move in 6 degrees of freedom. Range of motion is approximately 200 millimeters up and down, and 40 degrees of rotation. Now, because it's completely flexure-based, the repeatability is going to be below 0.1 micrometers. Here you see a closer view of this system, and we'll look at the architecture of this system shortly. So it's all flexure-based joints, and we have revolute joints at the base, which is where the actuation happens, and we have spherical joints, which are the red components in the arms. So this gives you a feel for the build volume of the system, which is about this size, and relative to the build volume, the workspace, for instance here in a vertical translation, is about 200 millimeters. And this is due to the fact that these joints can do a fairly large range of motion. Now we're going to zoom in and look at what this repeatability means. So we're zooming in to a scale below the micrometer, which you see on the left hand side, and we're marking a spot on this hexapod. Then when the hexapod moves away and comes back, the same point will be within 0.1 micrometers, which is what repeatability refers to. Kinematically, what happens in this robot? This is what it looks like in terms of these ideal kinematic joints. So you can see at the top we got the end effector with spherical joints. In the arms, there are several joints, and at the base here we have 6 revolute joints. So these revolute joints are the ones actuated. Halfway we have these spherical joints, and also at the top, at the end effector, there are 6 spherical joints. The flexure-based version of these spherical joints is what we can zoom in to. So this is what it looks like. So the flexure-based meaning no sliding or rolling contacts. And the components in this are these folded leaf springs. 6 folded leaf springs here that you see interwoven. And this particular design allows for 50 degrees of tip tilt motion and 20 degrees of pan motion. So there's in total 12 of these spherical joints in this entire thing. At the base we have the revolute joint, and the revolute joint is actuated. So we'll do an exploded view of that revolute joint at the base as well. It looks something like this. So here there's also a big flexure joint in there along with the actuation. This flexure joint looks something like this. It's based on a butterfly hinge design, and we'll look into more details of this one and also that spherical joint a bit later on. This is what the deflection of that system sort of looks like. It can do around 50 degrees of rotation. So this entire system first was optimized and modeled with computer software and optimized for getting a very high support stiffness. So let's look at these spherical joints. So as I mentioned, these spherical joints, there's 12 in total. They connect the arms to the platform at the top, and they're also located halfway. So the spherical joints look something like this. And now let's look at what's happening in this design. If you want to make a very simple flexure-based spherical joint, you could just get by with using the elementary design of 3 wires that intersect at one point. That's what you see right here. The intersection point happens within this blue cylinder. That doesn't matter because they intersect at a single point. For small excursions, you'll see that the rotational stiffnesses are really fairly low, but any translation is met with a very high stiffness because these wires do not allow stretching or compressing much because they have a very high axial stiffness. So translations, high stiffness, all of the rotations here, of the blue parts, have a very low stiffness, and that makes it behave like a spherical joint. So we can see that it can do some tip motion, some tilt motion, and some twisting motion. Now for larger ranges of motion, this is not the best design to make, and now we're getting more into flexure design ideas. Then it can be beneficial to replace the wires with something that does kinematically the same thing, but which has better properties when you're looking at how the stiffness changes with ranges of motion, so the nonlinear effects that I was talking about. So for instance, it's possible, kinematically it's equivalent to replace one of the wires with a folded leaf spring whose fault line coincides with that wire that we had. Exactly why that is goes too far for this discussion right now. Kinematically this is equivalent, but for deflections, the folded leaf springs offer some advantages. It brings several differences, because you can imagine that if the wire was located as we just indicated, you would have the connection points at the ends of the wire. Now with the folded leaf spring here, which is essentially just a blade with this fault line there, the connection points are at different spots. So the frame for this joint needs to accommodate that. So what we're doing here in this design, we're replacing all these wire flexures with equivalent folded leaf springs, like so, and this would also provide the motion of a spherical joint. Now, in the spherical joints in the T-flex that you saw, the ones that Marijn Nijenhuis optimized, it's not just 3 folded leaf springs, but it's essentially 2 of these on top of each other. Why 2 of each on top of each other? Is just to increase the range of motion, which is essentially distributing the total angle over 2 stages now. So a first render looks something like this. This one's got 6 of these folded leaf springs, and the ring halfway is that intermediate body. Now the challenge in designing this lies in a few things, but one of them is making sure that these folded leaf springs don't collide, and choosing the parameters such that the support stiffness doesn't decrease as much when the mechanism moves in its degree of freedom as it is doing right now. So this is what it looks like when it's tilted, when it does a tip motion and twist motion in the final design. Then after these spherical joints, we'll look at the revolute joints that are located at the base. So at the base there is, in total, there are 6 revolute joints with actuation built in. The exploded view looks something like this. And crucially, the actuator is this system. It's off-the-shelf actuator. It's an iron core direct drive motor. If you purchase this one, you get a separate stator and separate rotor, meaning there's no ball bearings in there. So you still have to provide the bearing of the rotor with respect to that stator yourself. And that gives us the opportunity to do it entirely flexure-based, meaning without introducing any friction and very little hysteresis. It's tricky because this being an iron core direct drive motor, there's permanent magnets there, and there's going to be a fairly large radial off-center force, a pull-in magnetic force, which sort of acts like a negative radial stiffness here. And this stiffness, this negative stiffness, needs to be counteracted by that bearing, which is the flexure that we're designing. So the gap that this particular actuator allows is less than 1 millimeter. So the radial stiffness of the flexure joint that needs to provide the bearing needs to be really rather large. Why iron core system? Well, then for the given volume you get a relatively high power density. What is nice about this one is that the stator is at the base, so meaning the coils are located at the base, so they're not moving, so the wires attached to the system are not moving, and in case cooling would need to be necessary, that's also easier to do because the coils are stationary. And now the bearing for that rotor with respect to the stator is provided by this design here. This is a butterfly pivot. This one was published on by Simon Henijn 20 years ago. Here you can see what that design looks like when it deflects, and it's more elaborate than just that simple cross flexure design that we saw. This one has a nice feature that the so-called pivot shift or the axis drift is really small. Why is that important? Well, it's important that the instantaneous center of rotation doesn't change too much because, as we mentioned, the radial misalignment that the actuator allows is fairly small, it was only the millimeter. And if you just take any flexure design, which is a revolute joint, then very often you'll see some axis shift, which is unwanted. So this design can be considered 4 cross flexures, these elementary joints, in series. And what the series stacking and the mirror symmetry does is that it cancels part of that axis drift that you would find in the single cross flexure. And also because it's several stages on top of each other, the total angle gets distributed over these intermediate stages. And that's nice because these nonlinear effects that cause the axis drift tend to depend on the deflection angle. So by distributing the angle, the nonlinear effect goes down tremendously. And what you can see here is that the center part of this design has a fairly large rigid body. So it could be relatively heavy. And because these are intermediate bodies, these are essentially unconstrained modes in a system, which could lead to problematic parasitic resonances. To counteract that, especially for that large rigid body right in the center here, it's possible to add an additional flexure that couples the motion of the end effector of this revolute joint to that center part. And this essentially constrains that rotational freedom that the center part still has. So there's an additional flexure on top of that to get rid of that unconstrained mode. That's also here what you saw on the design of the butterfly pivot as it was used in the T-Flex. This is a prototype of that actuator assembly. You can see the butterfly pivot with that synchronizing part on top of it. Here, if we make it move, what is interesting about it is that if you move it, you just feel the stiffness and the inertia, but there's no damping or friction-like effects. You can see that it's a fairly undamped motion. For the T-Flex, that's similar. This is first prototype. So this is still with the plastic end effector before going to the full metal version. Here you can see that you can touch it near the actuators, or you can touch it at the end effector. It's fairly undamped, and it's backdrivable, meaning any force that you apply to that end effector can be seen at the actuators. If the actuators were commanded to stay at a certain position in the current needed to accomplish that, you would be able to see any forces applied to that end effector, which can be beneficial for certain purposes. In the design phase of this T-Flex, computer models were used to find out what an optimal set of design parameters was. You can imagine that this model of a T-Flex contains a lot of elastic components, because after all, the system contains 12 spherical joints with each 6 folded leaf springs in it, and the nonlinear effects that contribute to the stiffness play roles. So just taking a full model of this is infeasible to simulate, and in particular to do optimizations with. So for that we have to do some model reduction and use beam elements that are a bit more efficient. So what do we mean with that? We have some mathematical formulations for describing the stiffness behavior of these leaf springs fairly accurately in a nonlinear sense. So we can describe what the pure bending and the pure torsion load case is, but also these combined load cases. We look at the effects of bending, of torsion, of elongation and shear, but also of warping. As an example, what do we mean with warping? It's fairly known, in particular in the civil engineering field. Here, if you take an H-beam that you see on the left-hand side and you apply a twist to it, so there's some torsion in that system. If the cross-sections are completely free to move, here if you look at that H-shaped cross-section, you can see that there's some warping of that cross-section that occurred. So warping is motion of that cross-section along the longitudinal axis, so along the x-axis in this case. For H-beams it's fairly well known, but it also happens for rectangular cross-sections on the right-hand side, such as a leaf spring. Now this thickness is a bit exaggerated, of course, but the warping happens here too, and it's something that happens for free when torsion occurs. Crucially, whenever the warping is restrained, so whenever the cross-section is constrained from moving at its end, which is fairly common for leaf springs in use because they're going to be clamped at the end, so there's just going to be a bigger part of material attached to it, then this warping cannot take place, and as a consequence, the torsion stiffness of this system will be much bigger. So these models that we have that describe the nonlinear interactions also capture these more detailed effects of warping, which is important if you want to have accurate models. Then for a bigger system, such as that T-Flex, it will contain a lot of design parameters, and to make an optimization feasible, it's necessary to reduce the design space a little bit. So here are some of the assumptions for the hexapod that were made. More details about this can be found in the thesis that I mentioned. Some of the examples are based on what you could find in literature, for instance. So literature on good topologies for hexapods. And one of the things that you can find, there are certain benefits for certain performance criteria when arm pairs are located in a single vertical plane. It can be good that the actuator pairs that are located at the base have their axes parallel to each other. Also, whenever the base joints are located close to each other and the wrist joints are located close to each other, it can have favorable properties depending on what you're optimizing for in a hexapod like this. So such assumptions can be used to introduce some symmetry in the system. And why is that important? Well, at least it reduces the design space. Then what does such a modeling approach look like? It's actually a sort of a staggered approach. So it starts with the kinematic model that you see here. And kinematic models are quick to simulate. So this is just a kinematic model assuming identical and ideal joints. This can be used already to get a sense of the relationship between the workspace that the robot can reach and the angles that are necessary in the joints. Here you see an example of such a simulation. So this could give you the trade-off between workspace and joint angles. Based on some sense of the joint angles necessary, it's possible to do a model for an individual flexure-based joint. So this is where the nonlinear stiffness comes in. Here you see one of these spherical joints, and knowing the joint angles that it should make, this one can be optimized, for instance, to provide a very high support stiffness. Now, knowing what this nonlinear stiffness looks like, it can be mapped onto that kinematic model. So it can be lumped onto that kinematic model at the locations of these ideal joints. And such a model won't take into account the compliance, for instance, in the arms or in the end effector platform itself, but it does take into account these nonlinear joint stiffnesses, which are a major contribution to compliance in the entire system. So such a system is going to be fairly fast to simulate, and it will still provide a good indication of the nonlinear stiffness of the entire hexapod. And that means it's possible also to see what the eigenmodes are in the actuation directions and also the parasitic eigenmodes. So as an example of that, here you see motion of this hexapod, which it shouldn't make, right? The actuators are not moving right now, but still this motion is in the system. So this is one of the parasitic eigenmodes. Ideally, the corresponding eigenfrequency is very high here. This one can be modeled because there's now these stiffnesses in the joints that model the non-ideal behavior. And also since the stiffnesses change over the range of motion, you would be able to get the changes in the frequency of these eigenmodes as the manipulator moves through its workspace. Another example of what you can find from such an analysis is an eigenmode like this one. Here you can see that the joints at the base are moving in a direction that they shouldn't. So this is because of some residual compliance in these base joints. And if the frequency associated with that one is high enough, it may not be a problem. So this is a staggered modeling approach that can be used to obtain a model that's sufficiently fast for doing optimization for such a large and complex system. To conclude, we looked at flexures and we see that it can be good for achieving highly repeatable motion and motion with very low hysteresis. For the designer, the challenge lies in the nonlinear characteristics. in particular regarding the stiffness that we just saw. And to deal with that, we like to use a lot of modeling approaches. These can be analytic, these can be numerical, to get a sense of the performance of a system. For the future, we can see all kinds of applications of these flexure joints, such as harsh environments. It would be interesting to know how flexures behave and how to improve them for very high load applications, for large strokes, as we saw, and further development of computational tools for designing these flexure-based systems. Thank you for your attention.